Welcome to this explainer. Today we're diving into the microscopic engineering that keeps our fastest, most capable devices from, well, bottlenecking or just straight up melting down. If you've ever wondered how manufacturers manage to connect billions of microscopic transistors to a motherboard without complete failure, you are absolutely in the right place. Let's dive in.
Here's our roadmap for today. First, the packaging bottleneck. Then, introducing flip chip technology, bumping and dicing, alignment and mass reflow, underfill and final packaging, and finally, why flip chip wins out.
All right, part one, the packaging bottleneck.
So here's the fundamental problem engineers ran into. As chips got infinitely denser, we're talking billions of microscopic transistors acting like tiny, bustling data cities. A massive bottleneck popped up. How do we actually connect all these microscopic circuits to a motherboard without causing an absolute traffic jam of electrical signals? I mean, you can have literally the fastest chip in the world, but if it can't talk to the rest of the computer efficiently, all that speed is completely wasted.
For years, the go-to solution was wire bonding. Basically, you tie these incredibly delicate gold or copper wires specifically to the outside perimeter of the chip. But, as you might guess, this method creates some major physical limitations. It totally restricts your connections to just the very edges, it traps heat under this thick mold compound, and honestly, having long, sweeping wires creates high electrical inductance. And in the high-speed electronics world, long wires are the absolute enemy of performance. Which brings us to part two, introducing flip chip technology.
Enter flip chip technology, or as the industry calls it, controlled collapse chip connection, C4 for short. This was an absolutely ingenious workaround that completely bypassed traditional wire bonding. Instead of keeping the chip face up and wiring up the edges, engineers realized, hey, we can just attach solder bumps directly to the active side of the die and then literally flip the chip upside down, kind of like a pancake. This connects its entire surface area straight to the matching substrate pads on the board. Game changer, right?
Now, this revolutionary C4 process happens in 6 highly precise, fully automated steps. It's essentially our manufacturing roadmap, taking us all the way from a raw silicon wafer to a finished, durable chip that's ready to power your device.
Let's zoom in. Part 3, bumping and dicing.
Step 1 kicks off with wafer bumping, because before we can attach any solder, we really have to prep those electrical pads. We do this through something called underbump metallization, or UBM. The factory uses sputtering or electroplating to lay down incredibly thin metal layers, usually titanium, copper, and nickel, directly onto the wafer bond pads. And this does 3 crucial things. First, it gives us a much-needed adhesion layer. Second, it acts as a diffusion barrier. And third, it creates this pristine surface that the solder can actually grab onto.
Once that UBM foundation is set, solder bumps, or sometimes copper pillars with little solder caps, are deposited across the entire active area of the wafer. And they do this using electroplating, screen printing, or ball drop tech. Finally, that deposited solder gets heated up, or reflowed, which turns them into these perfect microscopic spherical bumps replicated flawlessly millions of times across the whole wafer. It's honestly pretty mind-blowing.
All right, on to step 2. So now we've got this massive wafer covered in tiny bumps, but we need individual chips. First up is wafer thinning. The back surface of the wafer gets mechanically ground down, literally called back grinding, to hit an exact target package height. Once it's super thin, we move to dicing or singulation. Using ultra-precise blade saws or even lasers, the wafer is carefully sliced up to separate all those individual bumped dies without damaging the incredibly delicate silicon inside.
Part 4, alignment and mass reflow.
Okay, in step 3, we have to make sure that solder will properly wet and stick. To pull this off, we use a process called fluxing. The bumps are either dipped into a thin layer of chemical flux, or it's sprayed right onto the substrate, which strips away any pesky oxides that might mess up the bond. Then, high-precision automated optics step in to flawlessly align the die bumps to the substrate pads, and in one swift, incredibly precise motion, the machine flips the chip active side down and places it onto the substrate with sub-micron accuracy.
Step 4 is mass reflow soldering. The newly assembled die and substrate combo travels through a multi-zone reflow oven. As the heat ramps up past the liquidus point, a bit of absolute magic happens. The solder bumps melt and collapse just a tiny bit, which is where the controlled collapse part of C4 comes from. This creates a permanent, incredibly strong metallic bond between the chip and the substrate pads, all in one unified sweep.
Part 5. Underfill and final packaging. Now, right at this stage, we hit a massive physics problem. You see, silicon and substrate materials expand at totally different rates when they get hot. It's a phenomenon known as the coefficient of thermal expansion, or CTE. If we just left it alone, this mismatch would literally tear those microscopic solder bumps apart every single time you booted up your computer. No good. So step 5 brings in capillary underfill, or CUF. A liquid epoxy resin is dropped right along the edge of the die, and capillary action literally wicks it underneath to perfectly surround those little bumps. The whole setup is then baked to harden the epoxy, which flawlessly distributes all that intense thermal stress.
Finally, step 6 brings the whole thing together, taking us from the microscopic scale back to the macro scale. The package gets its final mechanical protection through encapsulation, usually a mold compound or a heat spreader lid applied using a thermal interface material. To wrap it all up, secondary BGA, or ball grid array, solder balls are attached to the bottom pads of the substrate. These are the much larger bumps that will eventually form the main board-level connection, tying the entire package right into your device's motherboard.
Which brings us to our final section, Part 6, Why Flip Chip Wins.
When you look at the specs side by side, it is crystal clear why flip chip completely dominates the industry. We're trading those perimeter-constrained wires for a massive, highly efficient array of bumps across the entire active area. We trade a long, laggy path length for a super short one. And we're swapping out poor thermal dissipation for excellent, direct thermal management.
But breaking that 10,000 barrier, that is the true game changer. The absolute most crucial point in modern computing is density. Because wire bonding only uses the very outside edges of the chip, it completely maxes out at roughly 1,000 inputs and outputs. But flip chip's full area array unlocks the entire surface of the die. That makes over 10,000 inputs and outputs possible on a single chip. It's a tenfold increase in bandwidth, which is exactly what makes the crazy complex processors and graphics cards we rely on today even possible. Beyond just the raw connection numbers, flip chip elegantly solves the electrical and thermal bottlenecks that really plagued older methods. Because those solder bumps give us a very short, direct connection, you get incredibly low parasitic conductance. That is absolutely vital for clean, high-speed signals. And since the chip is flipped upside down, the backside of the bare silicon is left fully exposed. So instead of heat getting trapped into a thick mold compound like in wire bonding, flip chip lets us attach a heatsink directly onto the die for phenomenal cooling.
Flip chip technology in the C4 process brilliantly solved the wire bonding bottleneck, paving the way for our devices to become exponentially faster and way more powerful. But it really begs the question, as our chips keep shrinking down closer and closer to the atomic level, and as we start stacking these dies up into 3 dimensions, what incredible manufacturing leap are engineers going to have to invent next to keep this revolution going? Thank you for joining me on this explainer, and keep questioning how the world inside your devices actually works.